analysis and design, ultimate strength design of beams, and I have copied few pictures from the two reference books which I mentioned on the title slide. Let me start recording. And the downloading of the attendance at 13 past 10. So I have copied few pictures in this presentation from 7th edition of M. Nadeem and 6th edition of McGregor. So this picture copied from 7th edition of M. Nadeem shows test on a simply supported beam loaded to failure. So you can see flexural cracks, widened flexural cracks, nearly vertical in the middle third of the span. So this test setup is under 4-point loading. 2 are the reactions and 2 are the point loads through which the load from the jack is being applied. So the middle third is pure flexure zone because shear force will be 0 in this span. So principal tensile stresses are nearly horizontal, so normal to them crack will appear. It is a reinforced beam and it shows a lot of ductility because too much sag and still beam is taking the load. This picture also is the one which can gives us idea that if the section is uncracked and beam is made of homogeneous elastic material, then if we apply bending stresses through the application of load on the beam, whether it is the UDL or the point load, at the maximum stressed sections, which is for a simply supported beam is the midspan, neutral axis is almost at the mid of the gross depth, and since material is elastic, section is uncracked, so in tension and compression stress strains are linearly increasing. And if I draw the strain diagram is also linear, and so is the stress diagram, because in tension and compression, if this quadrant indicates the strain versus stress in tension and the third quadrant indicates strain and stress and strain in tension, such kind of the classical material is steel. Steel has the stress strain in tension and compression, same behavior, and modulus of elasticity is also same in tension and compression. So the farthest fibers are at maximum strain and corresponding stress. So linear stress variation with respect to neutral axis is obvious. And if I want to determine the centroid of the volume which is present on this cross section above neutral axis, so I can easily determine that average stress multiplied by the cross section on which this average stress will be present, that can give me the point of application, that can give me the resultant force, which is compression, and it will be present at a distance, since half of the section is present, so this will be actually 2/3 of h/2. So 2 and 2 will cancel, so actually from neutral axis to the point of application of this, the resultant force will become h/3. So in this way, the internal couple between C and T and section is in equilibrium, C will be equal to T, and their lever arm in between will be H by 3 from this and H by 3 from below. So total it will become then 2H by 3. So this is what is shown here, that there is a couple internal resistance between compression and tension on this homogeneous elastic beam, and I can determine the internal resistance through T into JD or C into JD, because both T and C are equal. Then we can move on to a next picture, which is copied from 7th edition of M. Nadeem. In this picture, we are now indicating two beams, beam in picture B and C. So we can state that the midspan section of this simply supported beam is under evaluation, and at the midspan section AA, if beam is a plain concrete beam and we are in a very low stress range, the load application is less, so concrete has a compressive stress strain relation like this, and in tension it has very low capacity and it will fail. So if in compression I am just applying a low value of load and I'm on the straight branch, nearly straight branch, and in tension also I am very much low in magnitude and my tensile stresses are less than modulus of rupture, which will come over here, and then finally the concrete will crack in tension. So if I'm very low in stress magnitude in compression and tension, so again I will get nearly straight stress variation, because again the strain diagram will be linear and strain at the neutral axis will be 0, and away from the neutral axis, farthest from the neutral axis, it will be maximum. I will go through some assumptions on next slide, where we will talk about this strain and then stress diagrams. So in terms of plain concrete without reinforcement in a very low stress range at the midspan section, so you can imagine that these may be the stresses when beam is subjected to hardly its self weight. Very low bending stresses are present. Still you have almost a straight line, and the same you can say C is equal to T, and beam is uncracked. Although concrete is not a homogeneous or elastic, it is heterogeneous material, it will crack once modulus of rupture will come, and in tension it has very low capacity. But in very low load levels, we may get the same position. The neutral axis is right in the middle, and in compression and tension we have linearly increasing stresses. But as we increase the load magnitude, then modulus of rupture will come and crack will start appearing and they will start moving up. So is the location of the neutral axis. So earlier, if the neutral axis is right in the middle, then with the crack appearance and propagation, neutral axis will start moving up, and a very good uh, qualitative assessment will be the tip of the tension crack can't enter the compression domain. So when you find some cracks in the beam and their you can say their width and their length is visible, always above the tip of the crack there will be neutral axis, and because tension crack cannot enter the compression domain. So in this picture we can safely consider through this picture that neutral axis, because the crack is present here, will be almost over here at the tip of the crack. So then it above is the compression and below is the tension. So since it is a reinforced concrete, concrete contribution in tension is very small. So we are going to neglect this concrete contribution in tension. So entire tension is being given by the steel bars, and concrete role is to develop the bond between steel and concrete, and it is not allowing the bar to slip, so it is still holding the steel. The cover concrete is still responsible to prevent the slip, deformations on the bars, chemical adhesion between steel and concrete. There are mechanisms which are developing the bond. So composite action is still present, although the role of concrete in tension is negligible in at the section level, but its otherwise role is there. It is still protecting the steel from rust. It can still provide us resistance against direct attack of fire. It is still providing us the bond, the resistance against slip of the steel. So composite action is still present. So now, since the magnitude of stress increased, so we have moved up in the stress strain relation on the concrete, and some non-linearity in stress strain is getting visible. So you are seeing that it is now bending. There is some non-linearity here. So if I further apply load, I may approach the maximum strength of the concrete and the peak. And if I further increase the load, I may enter the softening domain, and eventually when it will soften to 85% of its peak, 0.85 of the compressive strength, we will declare that this is the crushing strength of the concrete, and now concrete can't take any more stress. But in this picture at the moment, it is somewhere over here. It is not still going very much high in the compression stress. So further increase in load may create more and more stresses, along with the increase in stress on the steel side. So still, in this case, when you will judge equilibrium, you will find that C is equal to T. Still equilibrium is established. The section is still providing the internal resistance. Beam has not yet failed. So keeping in view these pictures, now we want to discuss few assumptions which are also present in 2019 publication of ACI, and these are named as designed assumptions in Fluggear. So first assumption is equilibrium shall be established at each section. So in all these beams, when I want to check whether C is equal to T at this section, at this section, at this section, in all sections, this C equal to T must be present, otherwise beam will collapse due to failure at that section. So we are although looking at the maximum stressed section, but as a matter of fact, equilibrium shall be satisfied at each and every section along the span of the beam. Furthermore, plane sections remain plane after bending. Strain in the concrete and the reinforcement shall be assumed proportional to the distance from the neutral axis. So this assumption I can discuss on these pictures. Imagine that this beam before application of load will be almost straight. It was resting on the ground, or it was in contact with the ground all along its length, or even if it was lifted up on the supports, it was just subjected to its self weight. So if the section, mid-span section at that stage was this one, now once you start applying load on this beam, this section after load application has now been stressed to compression and tension, and there will be compressive strain in the top and tension strain in the bottom. So you can assume that if this was the section earlier, after bending the section will get this shape, and still it is straight. So the strain is linearly increasing with reference to the neutral axis above and below. So it will definitely bend due to load application, but it will still remain straight. So it is mentioned here, plane sections remain plane after bending. Strain in the concrete and reinforcement shall be assumed proportional to the distance from the neutral axis. So the layer farthest from the neutral axis will get maximum strain. And third is strain in the reinforcement is equal to strain in concrete at same level. So this is also very important to assume that if I am talking about the steel layer, sorry, suppose that there is a bar over here and it is surrounded by the concrete. So when I draw the strain diagram, and now I want to know that at this level, what is the strain in the concrete? So at this level, the concrete which is surrounding the bar as well as the steel bar will have the same strain. So on a cross section, if we examine, so if there are bars present, reinforcements, so the, and this is the distance of the layer from the neutral axis. So at this distance, this concrete or the bar, all of them are being strained to same magnitude. So it is mentioned here, strain in the reinforcement is equal to strain in the concrete at same level. So it means actually strains are proportional, which is stated here, strains are proportional to the distance from neutral axis. So once they are proportional, so all the layers are actually getting the strain with reference to the distance from neutral axis, whether they are the concrete layers or steel layers. So their strain magnitude will be equal. Then fourth is stresses in the concrete and steel can be computed from strains by using the stress strain curves for the concrete and steel. So this is also very important to note. As I mentioned earlier, that if this is the stress strain relationship of concrete and we know the stress strain relationship of steel, so when I have a strain diagram and I'm recording the strains in the cross section, so if I know that the concrete in the topmost fiber has a strain point 0001, because I am measuring the compression strain by putting the strain gauge on the top of the beam at the midspan section, and during load increment I measured that this is the strain value at top corresponding to some load. I will go to stress strain diagram, and if this is the 0.001 strain corresponding to this, I will measure the stress. If the stress will become 0.0003, I will say this is the strain, and then based on my stress strain relationship, this is the stress. So I will keep on measuring the strains, and the corresponding stress I can get from stress strain curve. Same is with the steel. If the steel over here has the strain 0.001, suppose, so since I have the idea of stress strain of my steel bar, so I will say this is the strain abscissa, and then corresponding to this, what is the ordinate, I will measure the stress. So I can draw from the strain diagram corresponding stress diagrams if I know the stress strain curves for the materials. Fifth is at failure, maximum strain at the extreme compression fibers shall be assumed 0.003 in case of concrete. So this is ACI assumption that concrete will be declared failed when the strain in that extreme fiber, topmost fiber, will approach 0.003, which we call as ultimate strain. So normal strength concretes, if you test them in laboratory and you measure the stress and strain relationship, it is quite possible that you get the softening at 85% of the peak corresponding to a strain which is 0.006 or even bigger. But ACI has introduced one limit to apply it for all concretes of normal strength, that the ultimate will considered will be 0.003, and based on this ultimate strain all our calculations will be done. So corresponding to 85% of the peak for normal strength concrete, we will use the ultimate strain of failure strain or ultimate strain of 0.003. This is the fixed value by ACI code. And the sixth assumption, as I said earlier, tensile strength of concrete, although that strength may be 1/10 of compressive strength, already 10% of the FC prime is there, but due to its meager contribution, it will be neglected. So in our equilibrium equations, in our internal capacity calculations, the tension side concrete will not be used in making the internal couple with the concrete. The relationship between concrete compressive stress and strain shall be represented by a rectangular, trapezoidal, parabolic, or other shape that results in prediction of strength in substantial agreement with comprehensive tests. So this is ACI provision 22.2.2.3, and actually on this provision assumption we are going to spend few minutes. Actually what we are going to do, actual stress strain relationship of concrete is non-linear and it is almost parabolic. So code has allowed us that you can replace this with the equivalent, either rectangular or trapezoidal stress. They are also lying parabolic, or even already it is more or less parabolic shape or other shape. But then the question is, requirement is prediction of strength should be in substantial agreement with the comprehensive test. So we are going to use the relationship between concrete, compressive stress and strain, and it will be represented by a rectangular or uniform stress block. So that we are going to do to make our equation simple. And finally, it will be proved that the simplified stresses are equal to the actual, and the answer in terms of compression force developed by the concrete will be equal whether we are using the actual or the simplified. So this is what we are going to discuss in detail in the coming slides. Before I discuss this uniform stresses or rectangular stress block, again let's discuss the stress strain curve of concrete. This is the peak strength. We also call it compression strength of concrete. Corresponding to this, there will be some strain. Normal concretes may have the strain 0.002, around 0.002 to 0.0025, corresponding to peak of the stress strain curve. We also call it compression strength, maximum strength, peak strength. So these words are used, and 85% of its peak, once it will approach, concrete is normally declared it is crushed, because now the crack has widened and no more resistance will be offered. And corresponding to this, ACI limits that the strain corresponding to this will be 0.003, and it will be at 85% of the peak strength. Now, question is that we want to determine compression force C due to the stress strain. We want to calculate the compression force C based on the stress strain curve of the material concrete. So the best thing is that I will calculate the area under this curve. I will do integration. If I know the mathematical model of this curve, I can do integration and I can calculate area under this curve. And then I will multiply this stress with the area on which it is present above neutral axis, and I can calculate accurately then what is the resultant compressive force C developed by the concrete. So this is the best option that whenever I have the idea that above neutral axis the material has this stress strain relationship, so what is the resultant resistance offered by that material? The best thing is I will do integration. I will calculate based on that stress strain curve what is the area under that curve, and that area under that curve will give me the stresses, and multiplying them with the area on which it is present will give me force. To do this analysis of the resultant force, there is one, you can say, methodology is given here, that if you will determine area under the curve by doing integration. For example, this is our problem and we have this curve with us. Its mathematical model is also with us, and we have done the integration and we got area under this curve. Now I will divide that area under this curve with the abscissa, which is the ultimate strain. Once I will divide that area with this abscissa, I will get the ordinate, and that ordinate will then be the average stress, which is exactly equal to the actual stress under the curve. So actual was this. When I got that by doing integration, I divided 0.03. Once I divided that 0.003, I got now the average value, which is, I am showing it with hatched. Now I'm getting this. So both are equal. So F average actually is equal to area under the curve divided by 0.003. So this is one step which is important because we are going to use this in the next slide. So actually what we have done exact calculation of area and then divided it with abscissa to get F average. And it is important to note for all concretes up to 30 megapascal compressive strength. All concretes, maybe you start from 17 megapascal. Normal in structural concretes, ACI recommends that the compressive strength of concrete should not go below 17.5 megapascal. So the concrete should have the compressive strength above or equal to 20 at least for good life and to get good durable concrete. 20 is the you can say normally used strength in low cost projects. However, ACI allows to go up to 17.5 megapascal, not less than that. So for concretes up to 30 megapascal, if you will get such curves for all of them for 20 megapascal, 21, 25, 29, 28, you got area under the curves for them. Then you divide them with the ultimate strain, which is fixed by ACI, is 0.003, you will get almost F average equal to 72% of the compressive strength. So up to 30, we have this fixed value. But if I am working on a higher strength concrete, like 50 megapascal, then I have to calculate it for that. First, I need to get the stress strain curve experimentally. Then I need to write a model for that curve, and then I will do the integration to get area under the curve. Then I will divide it with 0.003. Or for that concrete, what was the ultimate strain during experiment, I measured it. I will divide it with that ultimate strain to get F average. It will not be equal to then 0.72 C prime. So if I have this idea of F average up to 30 megapascal concrete, and I divide this F average with the crushing strength, which is 85% of the peak, this one, I will get a very important unitless ratio called beta 1. Greek letter beta is used, and with the subscript 1. So this is actually the ratio of F average, which is actual, based on actual curve. This F average is calculated over the crushing strength, which is assume 85% of the peak. I will get then this ratio, unitless ratio beta 1 equal to 0.85. But you will agree that it means this beta 1 is not fixed, since it means this beta 1 will remain valid for FC prime up to 30 megapascal. But if I have a higher grade concrete, then beta 1 will change, because this beta 1 is depending on FC prime, and FC prime up to FC prime 30 megapascal, F average is 0.72 FC prime. So we need to work out that for higher strength concretes, what will be the value of then this unitless ratio, which is a ratio of average strength over crushing strength. We will be using this beta 1 in next slide, so then I will talk about this ratio again. Now actually this is the total, I would say, flow chart to determine the internal resistance on a cross section. This is a very good slide because this will help you to understand total steps which we want to perform in order to get internal resistance of a beam at some cross section. Suppose beam is a simply supported beam, and we are doing this investigation at the midspan section, because in simply supported beam, midspan section will be at maximum stress. If beam is subjected to point load, PL/4 will be the maximum stress at the mid, at maximum moment at the mid. If the beam is subjected to UDL, WL²/8 will be the maximum movement at the mid. So we know that in simply supported beam, midspan section will be highly stressed. So maximum demand will come at the midspan. So corresponding to midspan, if beam has this section, it has a width B millimeters, it has a depth, gross depth H millimeters, and there is one dimension shown here, the distance of the steel bars from the compression face, which is given as which is shown with the alphabet D, small alphabet D, and named as effective depth. It is definitely less than gross depth. So in this case, it is quite easy to visualize that since beam is a simply supported, and I'm talking about this section, so tension will be at the bottom, beam will sag, and compression will be at the top. So It is shown here with the dotted line in neutral axis. And at this and now in this case, obviously the crack has appeared and crack have moved up. So tip of the crack may be somewhere here. So all the area below this dotted line is in tension, and above this dotted line it is in compression. And neutral axis now, as shown in the picture, is not exactly in the mid. It is not at h/2. It has moved up, and now it is almost at, suppose it is at h/3, or it has now the depth less than h/2. So this cross section at the midspan, we want to now investigate at how much the resultant C force can be developed by the concrete and the resultant T force developed by the steel. Because above this dotted line, the area present, which is concrete in compression, the stress in this area multiplied by this area will give me C with subscript C, compressive force developed by the concrete. And since we are going to ignore the concrete contribution below neutral axis, so all the tension is developed by the steel. So the stresses in the steel bars multiplied with the area will give me the tensile force. And since equilibrium is established, beam has not failed at that section, so C is equal to T. This is what we are actually trying to get finally. So once I will know the magnitude of forces, I will also be knowing their point of applications in the area where it is present. So if I know the point of application of them, I can also determine the distance between them. We call it internal lever arm. So knowing the distance between them, and since C is equal to T, I can calculate the internal resistance either by multiplying C into lever arm or T into lever arm. Both will give me same internal resistance. So in this picture, now we want to discuss the calculation of internal resistance, and I will now start from the strain diagram. Keep in mind all the assumptions which we have discussed on the previous slide. So ACI has given us assumption that the failure strain, maximum strain concrete can experience in the top fiber, which will be strained to maximum on the compression side, is 0.003. Plane section remain plane, assumption, and strains will increase linearly proportionally with respect to distance from neutral axis. So the strain diagram is linear, and this, when concrete will be crushed, is failing at the extreme fiber. Corresponding to that, what is the strain in the tension steel? So this is important. And since we have mentioned that strains will proportionately increase with reference to distance from neutral axis, so in each layer I can calculate the strain. On the tension side, since I'm not interested in the strain of the concrete because I know concrete has very low capacity and we are neglecting the concrete contribution. So I'm only interested in that layer where steel is present. So its magnitude epsilon S, S stands for steel, and epsilon Greek letter is used for strain. Here CU subscripts U ultimate and C for concrete. So knowing this strain magnitudes at the cross section, which is mid-span cross section, I can draw the stress diagram. Since for the material concrete, I know that in case of concrete, when 0.003 will come, it means concrete has approached 85% of its peak. So this will be the total stress strain curve, which has been rotated to 90 degree and is present here above neutral axis. So that's this top fiber, which is at 0.003, has softened, and it is this point, which is actually this point. And a fiber which is little inward at this moment will be at the peak, which is this one. And if I will want to draw the stress from the known strain in the steel, since steel is concentrated in one layer and steel obeys Hooke's law, so if I know the strain in the steel bars, I can multiply them with the modes of elasticity, 200,000 megapascal, which is the modes of elasticity of steel. I can get the stress in the steel bars, which are present in one layer in this picture. So this is actually the stress diagram from the strain diagram. Practically, if I'm experimentally trying to determine these uh, stresses in laboratory, I just need to measure strains at that section. And from strains, as I mentioned in the assumptions, that if I know the stress strain curve of the materials, from the strain I can draw the stress diagram. Then from the stress, knowing the area on which those stresses are present, I can get the force diagram. And if the point of application of forces are known to me, I can get the internal resistance by multiplying the forces with the lever arm. In this slide, there is one additional picture here in which you will find that only concrete is being replaced with a different picture. For steel FS, whatever was the strain multiplied by E has given us FS. But only concrete is replaced with the uniform stresses, uniform stress block of a depth A. In actual, the depth of neutral axis is C. But here in this picture, which is shown as equivalent to the actual, concrete is replaced with 85% of peak. Please put FC prime over here. 85% of FC prime, and it is present uniformly on the entire cross section. And it is claimed that both pictures, the actual one, which is little tedious because I need to integrate the area under the curve, and then I need to find out what is the point of application of C on this parabolic picture. And this picture seems little easy because I can multiply 0.85 C prime with A. This will give me the end with the cross section width B. So if I have the uniform stress present on area A into B, I can very easily calculate C. And this C will be applied at a distance from top A by 2. So very easily I got the C value by multiplying uniform stress with the area A into B. And I also got the point application of C, which is at A by 2, because stresses are uniform. But this will be only acceptable if the actual versus simplified picture will give me same C value and point of application of the C is not disturbed. So Whitney was the researcher who actually proposed and proved that we can replace the actual stress strain with this uniform stress block depth, and still we can get the answer exactly same. So in this way we can calculate the internal capacity with less effort. So how he proved that in both pictures the resultant C will be same and its point application will also be same. So this was actually the requirement that both pictures are equal. So if I will integrate the area under the curve and I get this C value from this uniform 85% of the compressive strength present on a depth A, if will give me gamma FC prime into AB, this C and this C should be equal. Then everyone will accept that rather than going through this rigorous exercise and doing integration, this seems more simple. If I know FC prime simply 85% of it and I can get A on which these uniform stresses are present, it is easier to get the C value. Furthermore, if I can prove that this beta C, which is the actual point application of resultant force from top, is exactly equal to A by 2, then everyone will accept that your proposed uniform stress block not only is giving the same C value, but also same point of application. So actual versus equivalent was proved by Whitney, and almost all international codes his proposal. Again, just to tell you, on an isometric view, we are actually looking for the resultant C and resultant T, and in between them the lever arm is giving me internal capacity. So the same picture on the previous slide is now shown with the on the isometric view, that on this area actually the uniform stress is present. The neutral axis depth is little deeper, but once I will use uniform stress block depth A, that is little shallower than C, and on that A into the width of the cross section, when these uniform stresses are present, I can determine C. But this C and C from this picture should be equal, and the point of application of this picture and from this picture should be equal. Now, how actually it was made equal, this slide can help us to understand that how Whitney actually proved that both the answers are same. Now look at the left picture. We already have done this exercise on the second or third slide of today's lecture, and we calculated F average by calculating area under the curve divided by 0.003, which is the failure strain. And we mentioned that up to 30 megapascal concrete, the actual stress strain diagram will give me F average equal to 0.72 FC prime. So this we have proved on the slide number, it was slide number 3. Let me go to that slide just to recall. This one, we did that exercise, that F average is actual area divided by 0.003. Now we move on to this slide. So it means on the left hand side of this equation, we are multiplying the F average with the actual area on which this F average is present. It is present on a depth C, which is depth of neutral axis, and on a cross section of width B. Now on the right hand side is Whitney's proposed. It is 85% of the FC prime, and this stress is uniformly present on a cross section of width B and on a depth A. So I am making both of them equal in order to claim that answers from both of them, because on the left hand side you will get C, on the right hand side you will get C. The left hand side C you will get from actual picture, and right hand side C you will get from the simplified picture. You made them equal. So now B and B on both sides will cancel each other. And once you will keep A on one side and bring other variables on the right hand side, interestingly, you will get that same unitless ratio which we have mentioned on the previous slide, that it is the beta 1 ratio of average over crushing. So it means what we can state that if A is equal to beta 1 C, then both C's are equal. So right hand side and left hand side calculation will be equal if your A has the value equal to beta 1 into C. So it means this beta 1 is based on FC prime 30 megapascal or below. So this relationship has the dependence on FC prime. So if I will change the FC prime above 30 megapascal, this beta 1 will change. But still this equation will remain valid. A is equal to beta 1C. I can improve beta 1 and still this equality will be maintained and both answers will be equal. So this is one way that if I want to use the uniform stress block depth, this A then will get the relationship with the actual neutral axis depth C based on this equation beta 1 C. Secondly, if the point of application of this CC in actual was beta C, now there is no subscript 1 with this beta. So if this is beta times the actual neutral axis depth, the point application of CC, and in the simplified picture, the point application is A by 2 because uniform stresses are present. So we need to make them equal. So I will say beta C will be equal to A by 2 if I will claim that from both pictures I will get the same lever arm. If I replace now what I have calculated the A as it is equal to beta 1C, So I'm putting A over here as beta 1 C divided by 2. On the left hand side is beta C. Now on the right hand side is beta 1 C over 2. C and C are present now on both sides. So I will be left with beta is equal to beta 1 over 2. And it is given over here. And since we have proved here up to 30 megapascal concrete, this is actually 0.85. Because 0.72 over 0.85 FC prime in cancel. So it is actually 0.85 into C, and this 0.85 I replace with beta 1. So if I will put that value up to 30 megapascal over here, so the answer will be that for concretes up to 30 megapascal, this beta will be equal to beta 1 by 2, and the value that we will get is actually 0.425. So I may say here that it is actually 0.425 into neutral axis depth, and over here A, if I put A up to 30 megapascal, A is actually 0.85. 0.85 divided by 2 will also give me 0.425. So in this way, in both pictures, not only I made CC from both pictures equal, I also have established that their point of application is also same. And this we have done up to concrete of strength 30 megapascal. Because F average, what we used is based on that finding that up to 30, F average will be 0.72 FC prime. Now, if you will question that, well, how we will change this beta 1. So beta 1 relationship for higher grade concretes we can determine, and one equation which can help you to predict beta 1 for concretes above 30 megapascal is given here. So it means if now you have a 37 megapascal concrete, so put 37 over here and get beta 1. If you have 40 megapascal concrete, put 40 here, get beta 1. If 50 megapascal concrete, put 50 here and get beta 1. Value of beta 1 decreases by 0.05. So from 0.85, it will go to 0.8. Then you will be using 37 over here. So for every 7 megapascal increase, it will drop by 0.05. However, a minimum value is 0.65. So for example, if I put suppose 70 megapascal over here and I get answer 0.6 or 0.55, you need to limit it to 0.65. So the every 7 megapascal increment will lower it by 0.05 and until you get to that value 0.65. So you can also find out this beta 1 by testing on concrete and then plotting the stress strain curve and then getting the area under that curve either through planimeter, use some geometrical rules or go for some mathematics and write the mathematical model of that curve, and then first prove that your mathematical model exactly simulates, predicts the experimental curve. There is a perfect agreement between your model and the experimental curve. Then do the integration to get area under the curve. Then divide that area with 0.003 or that ultimate strain what you have captured by actually performing the test that corresponding to 85% of the peak what was the strain. And then finally getting F average of that concrete which is above 30 megapascal. So this can be done in laboratory by performing test on the cylinders. For 30 megapascal concrete, if it this that stress strain curve for 40, for 50, for 100, so in this way you will get different stress strain curves. Obviously the ultimate strain and the peak strain will lower because higher strength concretes are more brittle, and this is what is the drawback of high strength concrete, that you need to add some fibers to control the brittleness. So I think I may stop for a few minutes at this slide. CR, can you open your mic?
Yes, sir.
My slides were visible?
Sir, not visible at the moment.
Yes, I just stopped the recording. But I could find some other, when I just came back to this slide, I got picture of a student. How is it possible? Because I was sharing my screen.
Sir, I think his camera was on by mistake.
Okay, okay, no problem. Okay. Okay, now I think meeting recording, just stopped at this point. So let's have a few minutes break and then I will resume.
Okay, sir.
This recording will be automatically uploaded. Section C and D recordings are also present. I can also share those recordings, but 2 hour recording with your section will be more comprehensive. So I think after break we will discuss the calculation of the internal capacity. So if meanwhile you have some queries or questions you can raise during this break time. You come to question. You can open your mic, and if you want to point out some questions, you are welcome. Now the slides. So this slide is very important because up till now we are talking about the section behavior, and in section behavior we are actually got the idea that I will be calculating C. I only focused at the moment that you will get C and T, and furthermore we said that in terms of strain that the crushing and the ultimate strength on in the top fiber will approach the softening, and this is the failure limit that the topmost fiber will approach 0.003. So we have mentioned all these steps, but we remained silent that when crushing will approach in concrete, at that stage, what was the status of steel? Whether steel has yielded or it is below yield, whether these bars will have ASFY, which is the limiting strain, and in USD that we will maximum use Fy up to Fy, the stress in the steel bars we will be using in our equations. So maximum T what we can use in our equations will be Ty, that is As into Fy. And although in steel we have a strain hardening and the failure is above that Fy, but we will limit the stress for our equations up to Fy in USD. So the question will arise that when we are talking about the ultimate stage and we want to fix the location of neutral axis at the ultimate condition, that when I have a strain diagram with the concrete in top at 0.003, which is the ultimate strain in concrete, and we will declare that crushing occurred because concrete roll will drop, because when C is equal to T, so if C will drop to 0 because of the crushing of the concrete above neutral axis, your equilibrium will not be present now and section will fail. But before dropping of C equal to 0, what was the status of tension steel? This is the question. Final failure will always be when crushing of concrete will take place. But before approaching that limit of crushing in concrete, we want to know that what is the strain and corresponding stress in the steel bar, and what was the neutral axis depth at that stage. So these are two important questions: neutral axis depth and the steel strain. These are two very important questions. Tensions, there are two cases broadly. Case one is that when concrete approached crushing and now C will drop to 0, but at that stage, concrete has earlier yielded, excessively yielded, or it just is has approached yielding. So when concrete approached 0.003, steel approached either strain equal to its yield strain or greater than that. To determine the yield strain of steel, it is very easy. For 300 grade steel, you will divide it with Hooke's law, modulus of elasticity. Hooke's law is applicable, and you will get the corresponding yield strain for grade 300 steel. For 420, even for 520, you can get the strain by dividing with E, the corresponding yield strain. So it means when you will say concrete is at 0.003, if it was grade 300 steel used in the beam, so epsilon S was either greater than or equal to 0.0015. This is one possibility. We call it case 1. Much desirable is that before crushing of the concrete, steel has excessively yielded, because yielding in the steel will create offensive sag, warning. It will improve energy dissipation, ductility of the beam. So it is always desired that steel should yield first, and then concrete will approach its crushing. Because once concrete will crush, it is end of story. But before that, whether we got warning, energy absorbed, factor of safety is there, more ductile failure. So all this will come if steel will yield first, will yield excessively, and then concrete will approach its crushing in the topmost fiber. The second case, which is undesirable, worst, that when concrete approached crushing in top, steel layer was not yielded. It was in the elastic range. So such beams will not deflect more, will not give us warning, and suddenly bursting of the concrete on the compression side will take place, and less ductile failure will occur. So without warning, a failure will be dangerous, and we call it over reinforced or compression controlled failure. And case 1 we will call tension controlled under reinforced failure. Case 1 means tension controlled under reinforced beams, and case 2 means over reinforced compression controlled beams. Both we can encounter while doing capacity analysis, but in new design you will not be allowed to design a beam over reinforced or compression controlled. In new design you will not be allowed to design case 2 beam. However, in review projects, a wrongly designed beam may be encountered, and while reviewing the capacity, then you need to comment that this beam is over reinforced, dangerous, and it should not be used as such. There should be some measures taken to improve the warning. Now we will talk about tension controlled under reinforced beams, or at the moment we are calling it case 1 beam, that tension steel is yielding at ultimate condition. Very simple to analyze, to design. Most simple and as well as desirable beam. So simple to write the equilibrium equation. For example, we are writing the equilibrium equation at a section. Always keep in mind that we are talking about a beam, suppose, and that beam is simply supported, and midsection of that beam is under review, and the midsection is maximum stressed, and at that stage the midsection may have a strain diagram like this, that the top fiber approached 0.003 crushing concrete, and steel at that stage, in this case 1, as we said, will be at epsilon y. So when concrete is crushed, steel is minimum at epsilon y. I mean, write like this: epsilon s, steel strain was minimum equal to epsilon y or bigger. So we are talking about this case one, that crushing occurred in concrete, and at that stage steel yielded. So the minimum strain at that stage will be, so if it is grade 300, the strain in the steel will be 0.0015 or bigger. In ultimate stand design, in my force equilibrium, if I know that steel has yielded and T is now actually calculated with area steel yielded, even my strain is bigger than 0.0015, if I'm talking about grade 300, I will not use the value of stress more than Fy. Suppose that if you get over here that your strain was, and you are working on a grade, suppose 300 steel. So when concrete is at 0.003 on top, steel strain was 0.005. So excessively yielded. It is grade 300 steel. Obviously, it is much more than 0.0015. But in force equilibrium, you will not be using stress more than Fy. You will still use As Fy. So in USD, in terms of steel, we will limit the stress to Fy. Even though my strain is over here or over here or over here, I will only use the stress magnitude maximum equal to Fy. Rest actually is like a factor of safety, that I'm not taking in account the strain hardening or more stress limit of the steel bar. So As Fy, and in terms of concrete, since we have discussed in the previous slide that Whitney's uniform stress block depth can be used and it can replace the actual CC. So the CC will be uniform stress present on a cross section of area A into B. So if this beam has a cross section like this, and this is the neutral axis, and this is the A value. So at the moment, as per Whitney's uniform stress block depth, we are saying that the CC is 0.85 C prime. Uniform stress is present on area B into A. In actual, the neutral axis depth is C. So this is the CC and this is T. Both are equal to establish longitudinal equilibrium, and the lever arm will be that steel bars are present at a height from top, at a distance from top to center of the steel as effective depth D. So the internal lever arm between CC and T will be then T D minus A by 2. because A by 2 CC will be present right in the middle of this uniform stress block, which is A by 2. So in between CC and T, the distance will be D minus A by 2, which is also shown on the previous slides, internal lever arm. So what I need to do is I simply will write the equilibrium equation T equal to CC. Since it is case 1, and I mentioned that case 1 means that tension steel yielded. Fy, all the steel will be yielded. Concrete grade will be known to me in the beam cross section. I will be knowing the width of the cross section. If it is a capacity analysis, I will be also knowing how many steel bars are present in the cross section and their area will be known to me. I will be also knowing what is the grade of the steel used in this project, in this cross section. In journal notes on the drawings, I can get the details about the material strengths, Fc prime, Fy. On the cross section, I can get details about the section width and gross depth and effective depth. So each and every detail is with me except where is neutral axis depth or Whitney's uniform stress block depths. So this case 1 beam, by writing simple equilibrium equation with all knowns except one unknown, that where is the neutral axis depth. I will keep that unknown on one side and I will bring all knowns on the right hand side, and with very little effort I can get the uniform stress block depth. And since we have proved that A is equal to beta 1 C on the previous slide, if I know the uniform stress block depths, I can also calculate the neutral axis depth, which is A over beta 1. So once I got the neutral axis depth with me, now I can write the internal movement resistance equations either in the T into lever arm or C into lever arm, because T is equal to CC and T is ASFY into lever arm D minus A by 2. And in terms of CC, it is 0.85 C prime A into B into lever arm D minus A by 2. So in both cases, I can get nominal capacities. Nominal means actual without reduction factors. So either you use T into lever arm or C into lever arm. Since we are working on ultimate stand design, so we want to reduce the capacity by applying the reduction factors. So for Flugger, in order to calculate ultimate movement resistance, either by using steel or concrete force to determine the movement resistance, T into lever arm into phi or C into lever arm into phi, I will put phi along with that equation, and phi in flexure used will be 0.9. This is the simple analysis of a beam with the known area of steel, with the known cross section, with the known material strengths details, and you are questioned to give us the capacity of the cross section. What movement resistance, ultimate movement resistance this beam can offer. So sectional details are provided to you, and you are asked to give the capacity. So it is actually a capacity analysis. I mentioned in my introduction lecture that we will have two kind of assignments. One is in field, one is that we will be requiring capacity of a section, other is we will be asked to design for this capacity. So when we are given with the cross section and we are asked to provide the capacity of the section, then we need to follow these steps. First, we will write the equilibrium equation. We will get the A and then C, and then we will write the moment equation to calculate the moment resistance. I will apply this information in one example problem. So just let me finish this slide and then I will apply this information, this discussion on one simple example problem. So this one slide actually tells us that in order to control the deflection, the best is that you increase the depth of the cross section, because deflection, immediate deflection, is inversely proportional to moment of inertia, and in moment of inertia you have h cube present, and in all your deflection equations you get EI in the denominator and span is a numerator. So bigger span will deflect more and deeper depth will deflect less. So deflection depends on span and conditions, and for different end conditions you know different equations to calculate the deflections. It also depends on load. W is a numerator, and Fy of steel. In reinforced concrete beams, it is important that in homogeneous elastic cross sections you have the simple equation which you use to calculate the deflections. Now we are talking about reinforced concrete beams in which there is a composite of concrete and steel. In reinforced concrete beams, Fy of the steel will also affect your deflection magnitude. And for high strength steel, deflection is more and more depth is required. So this is important statement that if a beam is reinforced with grade 300 steel, that needs less H relatively as compared to a beam which is reinforced with grade 420 steel. So for grade 420 steel, you will provide more depth to control the deflections, and this will be our point of discussion. And this table of ACI chapter 9 also reflects this, that when you want to decide the gross depth of the beam based on different end conditions, let's examine the simply spotted end condition, single span beam. When you have a grade 300 steel, you are asked to fix the gross depth H to control the deflections to fulfill the serviceability requirements that reflections are within limits. So H will depend on span of the beam divided by 20. But for grade 420, the required depth will get bigger because the denominator is reduced. And for grade 520, it is even further reduced. So it seems that with high grade steel, you require more depth to control the deflections in reinforced concrete beams. So in flexural members, if you will use high strength steel bars, in order to develop equilibrium and to control the deflections, because of higher grade steel, you will have higher yield strain limits, more rotation will be allowed. So you need more H, and as a matter of fact, more C value, compressive force, to develop equilibrium with tensile force. So more will be the grade, more will be the demand of gross depth in reinforced concrete beams. And also look at the end conditions. In one-way continuous slab, since one end is continuous, it is not free to rotate as it is in case of simply supported beam. Your H is reduced from L by 20 to L by 23. And when both ends are continuous, it further reduced to L by 26. However, in case of cantilever beams, to control the tip deflection, more demand is placed on H. So the heaviest H demand is for cantilever beams if we will examine the H requirement against 300 grade steel. So you can comment that in order to fix the H of a cantilever beam reinforced with grade 300 steel bars, highest H required will be L by 10, span by 10 for cantilever beams, and lowest required will be L by 26 for a beam which is both end continuous. It means interior beam. Suppose if you have 3-span beam, the middle span will demand L by 26, while the end spans will demand L by 23. And if the beam is single span, the demand will be L by 20. So we will talk about this in more detail, but before I finish today's lecture, I just want to draw your attention toward one simple example solution. Let me draw that beam on this slide, and I want you to attempt it at home. So in next lecture at start, I want to discuss its capacity analysis. You have to use the slides of today's lecture to solve this problem. It is not very difficult. Just try to attempt at home. Suppose you have a beam of cross section 300 by 450. It means 12-inch by 18-inch, right? And it is reinforced with 3 bars of dia number 25. Number 25 bars, if they are US customary bars, you can check them in design aids in tables. US customary bars. Number 25 has the nominal area 510 millimeters square. Assume that these bars are grade 300. So Fy of these bars is 300 megapascal. Assume concrete in this beam is of grade 20 megapascal. And this beam has a span 5 meter. It is simply supported. Bars are at effective depth from top. We will subtract some cover, concrete cover from below to center of the steel. I subtract 75 millimeter as the cover. So 450 minus 75. So the effective depth of this beam is then 375 millimeter. So I have given you width, gross depths, FC prime, Fy, span, and I'm asking you that can you tell me that this beam can take how much ultimate movement, and whether it is case 1 or case 2 beam. In this same presentation, I talked about case 1 and case 2. So this is your assignment, home assignment. And next lecture, section B, I want to know that how many of you have got MU of this beam. And then first I will discuss on that calculation which you will make. I will allow you to share your screen. If you have done this calculation, take a picture and then share, or on your notes, on your Word file or PowerPoint, solve it, and then you will be allowed to share your screen. So in this way, just let me know that whether you got MU of this 5 meter span beam, that how much load this beam can take. Have you noted this? Question? Section B.
Yes, sir. Note down.
गुड. तो ये इस तरह से हम इंशाल्लाह इस सब्जेक्ट को समझने की कोशिश करेंगे. So let me stop today's recording, and this recorded video will also be uploaded. So section B, next lecture में हमने इस equation, इस beam की capacity जो आप लोगों ने निकाली होगी उस पर डिस्कशन करेंगे, और ये स्टार्ट होगा आपकी लर्निंग का, बिगनिंग ऑफ योर लर्निंग, हाउ टू परफॉर्म कैपेसिटी एनालिसिस ऑफ रीइंफोर्स्ड कंक्रीट बीम्स. पहले आपने ये निकालनी है, ताकि मैं जानना चाहता हूं कि आप में से कितने स्टूडेंट्स अब तक की जो आज की प्रेजेंटेशन है उसको फॉलो किया है, कितने स्टूडेंट्स ने. राइट. इसको अपनी आप रेफरेंस बुक्स को भी देख सकते हैं. इसको अटेम्प्ट करने के लिए डिज़ाइन एड्स खोल सकते हैं आप. तो होपफुली नेक्स्ट लेक्चर वी विल attempt it after examining your answer. मैं एक टीचर फेलो भी हमारे साथ हैं, TF, मैं उन्हें भी असाइन कर दूंगा। आप अगर इसको अटेम्प्ट करें, और मैं एक फोल्डर बना दूंगा आपके फाइल्स फोल्डर के अंदर, which you can, where you can upload this assignment. So Allah Hafiz, because I have next lecture with section A.